Assalamualaikum. I am Nitika Kashuni. I am going to present the topic for Fulkerson algorithm for Max Flow, which is included in our course Design and Analysis of Algorithm. Now I want to share the list of contents. I will explain first of all number one, what problem does it solve, some basic terminologies, and the algorithm, the implementation using simulation, and implementation in IDE, then complexity analysis and applications and references. So first and foremost, what problems does it solve? As we said, it's for max flow problems, so it's to find maximum flow in a flow network from a single source is to a single sink is called terminal T. We can use this algorithm to solve problems in many different situations, like for example, that company might want to know what's the maximum number of trucks they can send from one place to another according to a roadmap where roads have different capacities. So, to find the maximum flow using the algorithm, we will need a simple directed graph to represent the flow networks as mentioned before it as to have one single source S and one single sink T, and all of the S have to have non-negative capacity for each S as paths or roads through which material can flow, and the vertices as junctions. We also be making a residual graph in which they only each share with the flow network are those whose flow can still be increased. The capacity of an edge in the residual graph is equal to the capacity of an edge the same edge in the flow network minus flow going through that is in order to make that decrease. We will add reverse edge. This is called cancellation. The capacity of the reverse edge will be increased every time we find a new flowing. Every time we find a new flow it, and in this visual graph we will look for augmenting path, which are simple path from the source to the sink, and we will try find the residual capacity, which is the smallest capacity of all H along P. And algorithm, so all put together we will make the residual graph such you metatarsal in an algorithm for each of them find the residual capacity help at a lot of them example which there still exist and augmenting the pay in the residual graph find the residual capacity and it to the maximum flow. Then for each is in the path decrease the capacity by the residual capacity if it's one of the original is. If it's one of the return is, then increase it by the residual capacity. Let's see by the algorithm in action now with this example. We first set all flow to 0 and the upper graph, the numerator shows the flow and the denominator shows the capacity. Then we go looking for an augmenting path, for example, this S A C T. We look at the residual graph and try to find the residual capacity, which is 8, and we add it to the maximum flow, and then we update the flow in the upper graph. Now we update the residual graph by adding back edge of capacity 8 first S A, then C, then C T, and we go looking for another of melting for example S B D T. Again we look in the residual graph for the residual capacity, which is 3, add it to the maximum flow and update the flow in the flow network. Then we do the same as we did before. We add the back edge to every edges in the path only, this time with a plus 3s b d d b d d t, and we go looking for yet another augmenting path, this time is A, B, C, T. We look for the residual capacity into the residual graph, which is 1. We update the maximum flow and the flow in the flow network, then we update the residual graph. And still the same way, adding back edge of 1 and updating the capacity for each edge, and we go looking for another augmenting path. Only this time we find none, as you can see. With the graph is there is no possible way to get to T from S. So the algorithm has terminated and is returning the value 12 for the maximum flow. And this is the implementation in IDE of this function. Finally, let's take a look at the complexity of the algorithm. The flow is at least increased by 1 at every iteration, because we are dealing with integers, so the while loop is repeated fm time at most, where fm is the maximum flow. Within the loop, we find augmenting path which run in stuff in hour of e, where e is the number of edge. We also do operation on value to update the maximum flow and the capacities of each, which run in time of 1. So, so for each iteration, it runs in time of e. This means that all in all, this algorithm runs in time of e times fm. So that was it about the basic implementation of the Ford-Fulkerson algorithm for max flow. I hope it helped, but it was somewhat clear. And the applications, water distribution pipeline, sorry, deeper matching problem circulation with demands, and references YouTube Introduction to Algorithm by Sherman G. for Greeks tutorials point to programmers. Special thanks to Linka Islam Ma'am, lecturer, Department of Computer Science and Engineering, Jagannath University. Thank you, everyone.
Assalamu alaikum. Welcome to my presentation slideshow. First, I would like to say something about myself because it is formality. First of all, I am Kondokar Jalal Mia. My ID is B. 18030519 and my presentation topics is Floyd-Warshall algorithm and course name design and analysis of algorithm lab and course code 2209 and course teacher Linta Islam Ma'am, lecturer of Computer Science and Engineering Department, Jagannath University. Now moving on. Things included. I will describe these things step by step. At first, a definition of Floyd-Warshall algorithm and properties of Floyd-Warshall algorithm and history and naming process of Floyd-Warshall algorithm. Example of the process algorithm, Java code, time and space complexity of a Floyd-Warshall algorithm, advantage and disadvantage, and comparison with other shortest path algorithm and application of this algorithm. Now, the first question of this algorithm, what is Floyd-Warshall algorithm? The Floyd-Warshall algorithm is a graph analysis algorithm for finding the shortest path between all pairs of vertex in a weighted graph. Now, the question is, what is weighted graph? A weighted graph is a graph in which each edge has a numerical values associated with it. Now, next, the properties of Floyd-Warshall algorithm. The first properties of Floyd-Warshall algorithm, this algorithm works for both the directed and undirected weighted graph, and it works positive or negative edge, but not work negative with negative cycle. The Floyd-Warshall algorithm is an example of dynamic programming. Now, what is dynamic programming? Dynamic programming is both a mathematical optimization method and a computer programming method. Likewise, in computer science, if a problem can be solved optimally by breaking into sub-problem and then recursively finding the optimal solution to the sub-problem, then it is said to be optimal substitution. Now moving on. History and naming. The Floyd-Warshall algorithm is also known as the Floyd's algorithm and the Warshall algorithm and the Roy-Floyd algorithm or WFI algorithm. History or background. The Floyd-Warshall algorithm is an example of dynamic programming and was published in it currently recognized from by Robert Floyd in 1962. However, it is essentially the same as algorithm previously published by Bernard Roy in 1959 and also Stephen Warshall in 1962. The modern formulation of the algorithm as three-nested for loop was first described by Peter Ingerman in 1962. Next, the process or approach. Let the given graph be. We can see we already know the Floyd-Warshall algorithm, an algorithm for finding shortest path between all pairs of vertex, right? Now we can go from 1 to 2 by distance 8, and we can go from 2 to 3 by distance 1, and we can go from 1 to 4 by distance 1, and we can go 4 to 2 by cost 4, and we can go 4 to 3 by cost 9, and we represent the information in adjacency matrix. And now we create a matrix of dimension n into n, where n is number of vertices the row and the column are indexes as I and J respectively. I and J are the vertices of the graph. Each cell Aij fill with distance from I vertex to J vertex. If there is no path from I vertex to J vertex, then we fill this cell by infinity. Now we can go from 1 to 1 by cost 0 because 1 to 1 is same vertex, and we can go from 1 to 2 by cost 8 and we cannot go from 1 to 3, so the distance is infinity, and we can go from 1 to 4 by distance 1, and we cannot go from 2 to 1, so the distance is infinity, and we can go the similarly the 0 1 infinity 4 infinity 0 infinity to 0 9. When k equal 1, then we can go throw by 1. So we can first the in degree of out degree of this vertex, the in degree of 1 is 1 and the out degree of 1 is 2. So we can go from 3 1 2 3 1 2 by cost 4 plus 8 equal 12, and we can go 3 1 and 4 3 1 4 by cost 4 plus 1 equal 5. Actually we will go from 3 to 2 by distance 8 by distance 12, and 12 is smaller than infinity, so we receive 12 and put in the matrix, and similarly 5 is smaller than infinity, so the 5 we receive 5 and set up in my and set our matrix. Next, when k equal to 2, then we can go throw by 1 and 2. So we can go from 1 to 3, and we can go 4 to 3. When we can go from 1 to 3, then the distance 8 plus 1 equal 9. When we can go when we go 4 2 3, then the distance 2 plus 1 equal 3. We can go from 1 to 3 by distance 9. So 9 is smaller than infinity, and put in the matrix, and 3 is smaller than 9, so we receive 3. Similarly, when k equal to 3, then we can go throw by 1 2 3. So we can go from 2 3 1 by cost 5, and we can go 2 3 1 4 by cost 3, and we can go 4 2 3 1 by cost 7, and we can go 4 3 1 by cost 13, and we cannot receive it because actually we can go 4 2 1 by distance 13, and here we can go from 4 to 1 by distance 7. So 7 is smaller than 13, so we receive 7 and put in the matrix, and similarly we receive 5 4 5 6 and put in the matrix. When k equal to 4, then we can go throw by 1 2 and 1 2 3 and 4. So we can go 1 1 4 3 by distance 10, and we can go 1 1 4 2 3. We can go 1 4 2 3 by distance 1 plus 2 equal 3 plus 1 equal 4. So actually here we can go from 1 to 3, and here we can go 1 to 3. The same distance same, so the destination same, and source and destination same. So the 4 is smaller than 10, so we receive 4 and put in the matrix, and we can go from 1 4 1 4 2 1 1 1 4 2 by distance 2 plus 1 equal 3, and we can go 3 1 4 2 3 1 4 2 3 1 4 2 by distance 7, and 7 is smaller than 12, so we receive 7 and put in the matrix. Algorithm of Floyd-Warshall algorithm. At first number we create n variable that nb a number of vertices, and we create an array that name is a and dimension n into n. For k equal 1 to n, for the statement is for iteration, and for I equal 1 to n, this statement for the row of the matrix, and for j equal 1 to n, this statement for the column of the matrix. If aij is greater than aik plus akj, then set aik plus akj in aij and return a. Java code. This is main method of this program. We declare two variable, the first number of vertices, and declare an array for matrix. We declare an object for scan, and we scan number of vertices, and scan the array for matrix by a nested for loop. And if I equal j, means if number of row and number of column is equal, then zero set adjacency matrix. And if I equal j, then then set 0 this cell and continue. If adjacency matrix ij equal 0, then infinity set of this cell in the matrix, and then we create an object for Floyd-Warshall class, and we call Floyd-Warshall method that define Floyd-Warshall classes and pass adjacency matrix and number of vertices. So now moving on, the Floyd-Warshall class. Here we declare and final here we declare an variable, and that name is infinity, and set 999, and we define a method that we call a main method, and it receives matrix and number of vertices. For int k equals 0, and k is smaller than number of vertices, and k plus plus this statement for the iteration, and for int I equal 0, and I is smaller than number of vertices, and I plus plus this statement for column for row of the matrix, and for j equal 0, and j is smaller than number of vertices, and j plus plus this statement for a column of the matrix. If matrix ik plus matrix kj is smaller than matrix ij, then set set matrix Ik plus matrix Kj in matrix Ij. And we call print matrix, and here print of the matrix, and by nested for loop, if each cell is infinity. If each cell is infinity of the matrix, then we print infinity. Otherwise, we print the matrix. And next, the Floyd-Warshall algorithm complexity. First, time complexity. There are three nested for loop, so each loop has constant complexity. So the time complexity of the Floyd-Warshall is O of n cube. For best case, average case, and worst case are same time complexity for this algorithm. If number of matrices is 10, then the complexity equal 10 cube equal 1000 comparison. It is huge time complexity. Then space complexity. Space complexity of the Floyd-Warshall algorithm is big O of n squared. Now moving on, advantage and disadvantage. Advantage of Floyd-Warshall algorithm. Floyd-Warshall algorithm helps to find the shortest path in a weighted graph with positive or negative edge weight. A single execution of the algorithm is sufficient to find the length of the shortest path between all pairs of vertices. It is easy to modify the algorithm and use it to reconstruct the path. A version of the algorithm can be used for finding the widest path between all pairs of vertex in a weighted graph or transitive closure of a relation R. That is disadvantage of Floyd-Warshall algorithm. The first disadvantage of the Floyd-Warshall algorithm is it is huge time complexity. And next, it can find the shortest path only when there are no negative cycle. And it does not return any details of the path. And next, comparison with other shortest path comparison with other shortest path algorithm. The Floyd-Warshall algorithm is a good choice for computing path between all pairs of vertices in density graph, in which most or all pairs of vertices are connected by S. Now, what is density graph? Density graph is a graph where the number of edges is approximately equal to the square number of vertices. For sparse graph with non-negative edge weight, a better choice is used to die-Custis algorithm. From each possible starting vertex, since the running time of repeated die-Custis is better than big O of E B plus B square log B. The running time of the Floyd-Warshall algorithm when is significantly smaller than big O of n cube. And next, for sparse graph with negative cycle, with negative cycle, but not for sparse graph with negative S but not negative cycle, Johnson algorithm can be used with the same asymptotic running time as the repeated die-Custis approach. Application of the Floyd-Warshall algorithm to find the shortest path. Is a directed graph. To find the transitive closure of directed graph. To find the inversion of real matrix for testing a graph is biopart or not, and optimal routing. Reference that I use in my presentation: Geeks for Geeks and Programize, Wikipedia, Google, and YouTube. Thanks to Alinta ma'am and everyone for having patience. So thanks, ma'am.
Okay, good afternoon, everyone. So I am here to talk about Euler path. First of all, I would like to introduce myself. I am Satyajit Ghosh. My ID is B180305043. Course name is Design and Analysis of Algorithm, course code CSC 2210. These are the things that I have included in my presentation slide. In the beginning, I will talk about the history behind the Euler path, then definition, then properties, examples, algorithm, implementation, then complexity analysis, and in the end, references. Okay, let's take a minute to remember the history behind the Euler path. So Euler path first discussed by Leonhard Euler while solving the famous seven bridges of Königsberg problem in 1736. The seven bridges of Königsberg is a historically notable problem in mathematics. Its negative resolution by Leonhard Euler in 1736 laid the foundations of graph theory and prefigured the idea of topology. The problem was to devise to a walk through the city that would cross each of these bridges once and only once. Okay, now the definition part. An Eulerian trail or Euler walk in an undirected graph is a walk that uses each edge exactly once. If such a walk exists, the graph is called traversable or semi-Eulerian. Similarly, an Eulerian circuit or Eulerian cycle is an Eulerian trail that starts and ends on the same vertex. The term Eulerian graph has two common meanings in graph theory. One meaning is a graph with an Eulerian circuit, and the other is a graph with every vertex of even degree. These definitions coincide for connected graphs. For the existence of Eulerian trails, it is necessary that 0 or 2 vertices have an odd degree. If there are no vertices of odd degree, all Eulerian trails are circuits. If there are exactly two vertices of odd degree, all Eulerian trails start at one of them and end at the other. A graph that has an Eulerian trail but not an Eulerian circuit is called semi-Eulerian. Okay. Now properties. An undirected graph has an Eulerian path if and only if exactly 0 or 2 vertices have odd degree and all of its vertices with non-zero degree belong to a single connected component. A directed graph has an Eulerian path if and only if at most one vertex has out degree minus in degree equal to 1, or at most one vertex has in degree minus out degree equal to 1. Every other vertex has equal in degree and out degree, and all of its vertices with non-zero degree belong to a single connected component of the underlying undirected graph. Okay. Here is an Euler path example. 5 vertices are there: A, B, C, D, and E. But there are two vertices with odd degree, which are B and C. We can start path from any of them. Let us start from vertex B, and vertex B contains a self loop. So the traversal would be B to B, then B to A, then A to D, then D to C, then C to again D, then D to E, and E to B, and B to C. There are no more edges left, so we stop here. So final tour is B, B, A, D, C, D, E, B, and C. So you can see that we traverse every edge exactly once. This is the main definition of Euler path. Okay, this is the same example which I described in the previous slide, but in this example we start our tour from the vertex C. Previous example, we start our tour from the vertex B. And the traversal goes as follows. We start from C, then C to D, again come back to C, then C to B, and B has a self loop. So we traverse B to B, then B to A, then A to D, and D to E, then E to B. So final tour is C, D, C, B, B, A, D, E, B. Okay, this is an Euler circuits example. Here is also 5 vertices are there, but 2 of them have even degree. Which are the vertices B and C. We can start our tour from any of them. In this example, we start from C, then we traverse C to D, then again come back to C, then C to B, and B contains the self loop. So B to B. So we first traverse B to B, B to A, then A to D, then D to E, then again E to B, then B to C. So the final tour is C, D, C, B, B, A, D, E, B, and C. Okay. This is another example of Euler circuit. We start from we start our tour from C. We start our travel C, then C to D, then D to E, then E to B, and B contains a self loop. B contains a self loop. That's why B to B, and B to then B to A, then A to D, and D to C. Okay. Now algorithm parts. Fleury's algorithm is used to display the Euler path or Euler circuit from a given graph. In this algorithm, starting from one edge, it tries to move other adjacent vertices by removing the previous vertices. Using this trick, the graph becomes simpler in each step to find the Euler path or circuit. Fleury's algorithm is very important in allowing us to be able to construct an Eulerian trail given an Eulerian graph G. Now the algorithm part. Fleury's algorithm is used to display the Euler path or Euler circuit from a given graph. In this algorithm, starting from one edge, it tries to move other adjacent vertices by removing the previous vertices. Using this trick, the graph becomes simpler in each step to find the Euler path or circuit. Fleury's algorithm is very important in allowing us to be able to construct an Eulerian trail given an Eulerian graph G. Okay. We have to check some rules to get the path or circuit. First of all, make sure the graph has either 0 or 2 vertices. If there are odd vertices, 0 odd vertices, start anywhere. If there are 2 odd vertices, start at one of them. When there are two edges, one is bridge, another one is non-bridge, we have to choose non-bridge at first. So a new thing strikes in our mind, that what is called bridge. So I want to drop some words about bridge. An edge in an undirected connected graph is a bridge if removing it disconnects the graph. For a disconnected undirected graph, a bridge is an edge removing which increases number of disconnected components. Okay, consider this image. It will give us more clarification about bridge. If we remove the edge between node 0 and 3, then there will be two connected components, which are 0, 2, 1, 2 and 1, and 3 and 4. If we remove the edges between 3 and 4, it will also increase our connected components by 1. And there will be two connected components, which are 0, 2, 1, and 0, 2, 1, 3, and only one node is 4. Okay. In both cases, they'll increase our connected components by 1. So these two edges are bridges. Now, if we remove the edge between 0 and 2, or 1 and 0, or 1 and 2, they will not increase our connected components, because after removing these edges, all nodes will still be connected to each other. So the bridges are 0 to 3 and 3 to 4. Now I again return to Fleury's algorithm. The idea is don't burn bridges, so that we can come back to a vertex and traverse remaining edges. For example, let us consider the following graph. We will not traverse any edge which is bridge at first. I will traverse then in the end if I can. Okay, there are two vertices with odd degree, 2 and 3. we can start path from any of them, but we cannot start 2 from 3, because if we start from 3, we firstly we have to traverse a bridge which is 3 to 2. So we start so we can start from the node 2. Okay, then we traverse from vertex 2 to vertex 0. Then because it will help us to convey which edges are already used on. Okay, next traversal from 0 to 1 and remove the, okay, next traversal from 0 to 1, then 1 to 2. Okay, and remove the edge for the same reason. We are removing the edge because it will help us to convey which edges are already used tones. So that's why I am removing these edges to convey which edges are already used tones. Okay, so there is only one edge from vertex 1, so we pick it and remove it and remove to vertex 2. Euler 2 becomes finally 2 0, then 0 1 1 and 2 to 2 1 1 then 2. Again there is only one edge from vertex 2, so we pick it, remove it, and move to vertex 3. Euler 2 becomes 2 0 0 1 1 2 2, and in the end 2 to 3. Okay. Okay, note that we traverse every edge exactly once. This is the main definition of Euler path. Now I will discuss about the algorithm. This part is for finding the this part is for finding the starting vertex to start Fleury's algorithm. At first I am calling a function from main function, from main function algorithm. Okay, at first I am calling a function from a main function algorithm. Okay, I traverse every vertex which denoted by I in the graph, and initially the variable deg, which means degree, with I initialize it with 0. Okay, in nested loop is for checking is in nested loop is for checking the adjacent node or vertex of I, vertex of I. Obviously if adjacent node exists, then it will increase the degree by 1. Okay, it will increment the degree by 1. Then if degree is odd, then it will return the it will return the starting vertex to start the Fleury's algorithm, else it will return 0 and the code will exit here. That it means that there is no Euler path possible because there is no odd degrees. Okay. Okay, I again call a DFS function to count the number of nodes. We all know that DFS is recursive in nature, and here the function has 3 parameters, which is previous, which means the parent node. Another parameter is start, which means current node, and the last one is visited array, which will mark the nodes which are already visited, and I will not visited them twice. Okay, now here uh, uh, first of all I visited the start node, means current node, true. Okay, that means the node is already visited, and count and I initialize count with 1. Okay, okay, now here b contains the adjacent node of current node, adjacent node of current node in the graph. And if adjacent node is not parent, I denoted if with u, and if u is not visited, then I will call DFS function with parameter of start, u, and visited array. Here in this DFS function, now the current node will become parent node and the adjacent node will become the current node. Okay, and the visited array I am passing. After the okay, the DFS function will return the count of nodes which I am storing in the count variable. Okay, after the DFS function I am calling isBreeze function. The function um, which is the function I'm calling it the boolean function which is isBreeze from main function. The function will return true if there is a breeze and start if there is a breeze between the start node which is u and the ending node which is v, and return false if there is no breeze between u and v. Then I traversed all adjacent node of v, and if there is adjacent node then I will increment the degree by 1. Before it I initialize degree with 0 because I will check for all nodes individually. Then if degree is greater than 1, it means there is a bridge from node u to v, and return true. Otherwise it will return false. That means there is no bridge between u and v. Now the Fleury algorithm function, okay, now the Fleury algorithm function which contains a parameter which is starting vertex. Starting vertex. This starting vertex I found from the function find start vert function which I already described. Okay, this Fleury algorithm function will display the Euler path. Firstly, I declare a variable which is edge. If which is edges. If there is n nodes, then number of edges would be n minus 1. Okay. Then I declare a variable v count which means the vertex count, which it will store the number of vertices. Then I will traverse all vertices which are adjacent, which are adjacent to start node means current node. Then I will make visited array fill with false value. I make visited array with false value. Okay, then I am calling a function isBreeze with the parameter of start node and adjacent node v. If these two nodes form a bridge, the isBreeze function will return true, and I will decrease vertex count by 1 because I will not use this vertex now. Then I storing the count of nodes in CNT variable by DFS function which I have already described before. After this, if difference between the count and vertex count difference between the count and vertex count is less than equal to 2, then I'll print the edge. I'll print the edge. I'll print the edge and I can traverse those edges. Then I am calling again isBreeze function. If it is returns true, then I will decrease the number of vertices by 1. This means this edge is already used and remove it. Then I will decrease the number of edges by 1. The again recursively then I will decrease the number of edges by 1. The again recursively calling the function Fleury algorithm with the parameter adjacent node v. By calling this function recursively, it will print the desired Euler path, and we will see the output in the console. Okay, now the implementation. Okay, first of all I declare a class named graph. Then I declare a private variable vertices and array list which will contains the adjacent element of graph. Okay, and then I declare a constructor to initialize vertex count, and calling init graph for initialize adjacency list. Here is init graph. It will initialize adjacency list. Okay, add edge function for adding edges, and the remove edge function for removes edges uv from graph. The main function that print Eulerian trail. This is the function which will print the Eulerian trail. If first it first finds an odd degree vertex and then calls print Euler util function to print the Euler path. Okay, this is the print Euler util function. It will print the Euler path and it will remove the edge which I already used. Then again it will recursively call print Euler util function with the adjacent element of node u. Okay. Mm, again okay, the print Euler util function will works as follows. First of all, the node which is the current node, I will check the all node which is adjacent to the current node and storing it in the variable v. Then I am checking that u to v the edge is valid or not. What is this what is that means I will check that the that u to v is form a bridge or not. If it is form a bridge, then I will not traverse on that way. I will traverse in different way where is not which edge not contains a bridge. Okay, if it is true, then I will print that u to v that form a uh, Euler path. Then I already used that edges. Then I will remove the edges. Then I am recursively calling the again Euler util function. Okay, this is the DFS function uh, for counting the number of edges. First of all, DFS function has two parameter. One is integer variable v and a boolean array for mark the node which already have visited. Okay, first of all, I visited the node as true. Then I initialize count with 1. Then I traverse every adjacent element of v. Then if adjacent element of v is not visited, then I will call DFS function with the adjacent element which will become the current element and the visited array. And after traversing all of the node, then it will return count, and the count will come to this DSS function that will and add to this count, and it will store to this count. Okay, and in the end this the count is the it will return the count. Okay, this is the main function uh, of Fluidis algorithm. Okay, now first of all, I am taking input from user. This n is for how many nodes are there. Then I am initialize graph g1, or you can tell this I resize the graph with n. Then I traverse okay, then I then mm, okay, then I take two nodes as input u and v. And I add those edges u to v. And after this input taken, then I will call I'll call the print Euler tool. Okay, this function will print the Euler path if there is a Euler path possible, or if there is a Euler path possible. Okay, now the complexity. Time complexity of the implementation is order of v plus edges, v plus e square. Here v means vertex, plus e means edges. Okay, the function print Euler util is like DFS, and it calls its valid nest eggs, which also does DFS two times. Time complexity of DFS for adjacency list representation is order of vertex plus edges. Therefore, overall time complexity is order of vertex plus edges star multiply with vertex plus edges, which can be written as order of edges square for a connected graph. And space complexity, order of vertex square. Okay, now the application. Eulerian trails are used in bioinformatics to reconstruct the DNA sequence from its fragments. They are also used in CMOS circuit designed to find an optimal logic gate ordering. There are some algorithms for processing trees that rely on Euler tour or the trees, where each edge is treated as a pair of arcs. Okay, references that I have used: Geeks for Weeks, Wikipedia, Stack Overflow, Tutorials Point, Google, YouTube. Okay, thank you everyone for thank you everyone for be patient, and thank you Linta ma'am, thank you Sonia ma'am to giving me the opportunity to describe about the Euler path.